let's see where it is next time. Okay, yeah, the usual question to you, is there something you want to discuss concerning the content, what you're supposed to read? It was about the Dirac equation, and it was, I mean, mainly meant that you remember from relativistic quantum mechanics or quantum field theory, what the Dirac equation was about. So, questions? Then maybe let me summarize the essential points without now going too much into detail. What this thing was about is to tell you a Dirac equation is an equation for a 4-component object, and these 4 components have the information content of a particle with spin up, a particle with spin down, an antiparticle with spin up, and an antiparticle with spin down. So four components. The other thing I usually try to stress is, again, how much information is in these equations. Now usually, and one can count this information like in classical mechanics. In classical mechanics, if you have 1 degree of freedom, you are interested in a second-order differential equation, which gives you the equation of motion. Yeah? Newton's law is of second order concerning the coordinate. Now this is then 1 degree of freedom, and it has 1 second-order differential equation. Now, before I introduced here the Dirac field, we also discussed the Klein-Gordon field. This is now a 1 degree of freedom where per space point I can excite, on every space point I can excite this field, and it satisfies a second-order equation in time. And it couples always to the next neighbor by these spatial derivatives, and it also has, in a sense, a self-coupling by the mass term. But again, this was 1 field, which was actually real valued, and it satisfies per space point a second-order differential equation. So this is again 1 degree of freedom, however, now 1 degree of freedom per space point, not 1 general like in mechanics. Now the Dirac equation is actually a first-order differential equation in time. However, it is a first-order differential in time for a complex object per entry of this 4-component spinor. So for every degree of freedom for spin up of the particle, spin down of the particle, spin up of the antiparticle, spin down of the antiparticle, it satisfies a first-order differential equation, not like in the other cases, but it is always for a complex valued amplitude. And a complex field has 2 degrees of freedom. So in total, if you split that in real and imaginary part, we have now 8 equations for real and imaginary parts of these 4 components. We have 8 equations of first order in time. And you know, I think, how to solve differential equations. For example, a second order differential equation in time, one solves that numerically by rewriting it into first order differential equations in time. For example, by introducing position and momentum. I'm now back to mechanics for a moment. So with position and momentum, I have 2 first-order differential equations in time to describe 1 degree of freedom. One is that I relate the velocity to the momentum, and one I relate the derivative of the momentum to the force. And that's the same thing here. We have 8 equations in total for real-valued objects for the Dirac equation of first order in time, which describes 4 degrees of freedom per space point. Okay, so the counting of degrees of freedom and so on is completely okay in spite of the fact that the Dirac equation is first order in time and the Klein-Gordon equation is second order. But for the Dirac equation, even for 1 degree of freedom, one always has real and imaginary parts. This accounts for that I have as many degrees of freedom as I would think I have. So that's the first thing, that one understands the content, at least the elementary content of the Dirac equation. The second thing where I think spend most of these pages with is showing to you what is helicity and what is chirality. Let me summarize this one more time, because this is really important from a conceptual point of view. Let me start with helicity. Helicity is basically the question how the spin is oriented relative to the momentum of this state. If the spin is aligned with the momentum, points in the same direction as the momentum, one basically says this is a right-handed state and this has helicity plus. So basically, I mean, if I identify here with my right-hand rule the spin vector with the understanding that I have a rotation according to my right hand, of course this is, well, not what the real physics is about, because spin 1/2 one cannot view as a orbital angular momentum, but I mean just for the sake of science, not of the absolute values. So if something travels in that direction and the spin points in that direction, in the same direction, and then the angular momentum is like this, or the rotation is like this, this means it's right-handed concerning helicity, or it has positive helicity. And if the spin points opposite to the flight direction, this is negative helicity. Okay, so helicity is something A, very intuitive, B, for the free Dirac equation, this is conserved. If a particle travels with positive helicity, this does not change in time. It does not suddenly flip back and forth. It's fixed once and for all. In a free theory, if no interactions act on this one Dirac particle. So helicity is intuitive, helicity is conserved, and however, helicity depends on the frame of reference. When I say something is traveling in that direction, I can reverse that statement by traveling faster than this object. And then this object, in fact, travels from my new frame of reference, travels in the other direction, because it's left more and more behind. The spin does not change when I change my frame of reference relative to this traveling particle. So the spin, for example, still points in that direction. So first I had a particle traveling here. I'm here in the rest system of this classroom. Spin points, say, in the direction of traveling. Now I travel faster than this object. I look back at the object. Spin still points in that direction, but the object flies in the other direction. I should always use the right hand probably. Which means the spin points now opposite to the flight direction. Which means the helicity is conserved when I view that from one fixed frame of reference, but it's not absolutely given by a property of my particle, but it's rather the property of this particle relative to my frame of reference. The helicity can change when I change the frame of reference. So the three properties: helicity is intuitive, helicity is conserved, but depends on the frame of reference. This I want to contrast with chirality. First of all, chirality is unintuitive. Chirality, one gets a chiral Dirac field just by projecting out the upper or the lower two components by using these projection operators with a gamma 5, and then one just takes from the whole information contained in these 4 components spinor object, one just takes 2. And this is then the chiral, either chirally right-handed or chirally left-handed part of this spinor. And there is not more intuition to that. It's just formal. So it's unintuitive as compared to the helicity. In addition, actually, it's not conserved. If I have a Dirac particle, this basically always has right and left-handed, concerning chirality, right and left-handed components. So it's not conserved in time, but, now comes the third point, I can formulate this in a Lorentz invariant way. It does not depend on the frame of reference. Independent of the frame of reference, my right-handed projector always takes the upper two components of this spinor, and the left-handed the lower two in this representation, how I have written down the gamma matrices. So chirality is unintuitive, not conserved, but Lorentz invariant. And now so far I talked about non-interacting particles. When it comes to interactions, one formulates interactions locally. We have local quantum field theories. We do not want that interactions are spread over a distance, at least the things we write down in the Lagrangians. We can have exchange particles transporting information from one point to another. However, then these exchange particles couple to my original particles locally. In the end, it boils down to local interactions. And the reason is that if something is non-local, you easily mess up causality and microcausality. You easily can construct situations where you transmit information faster than the speed of light, and this is unphysical. And the easiest way to avoid that is to have local field theories. Then every interaction happens locally, and if it's locally, then you cannot violate Einstein's rule that information cannot travel faster than the speed of light. If I have a local interaction, however, this cannot depend on how fast my particle moves. And therefore helicity, which obviously depends on my frame of reference and whether it moves or not, and whether it moves in which direction relative to my spin, this is nothing which I can formulate locally. However, chirality I can. Chirality one can formulate in a local way, so this is very, very well tuned for local field theories, and it turns out that in a weak interaction it plays a role. The weak interaction couples only to left-handed particles. The W and the Z bosons, they couple to left-handed particles and actually to right-handed antiparticles, but not vice versa. And this handedness now refers to chirality. What does that mean? Well, this means, of course, at one instant in time, I can focus on the two out of these four components of my Dirac particle. So, for example, I can create excitations there in the left-handed sector, and then the particle which I create, this travels, and then its chirality changes, mixes. That's fine. However, when I have produced it, there the chirality matters. There it's the chirality and not the helicity. This is not in contradiction to that the chirality is not conserved in time. And it's also not related to whether we can easily imagine what chirality is or not. The interaction is just made like that. But now comes one thing, I discussed that also in the notes. There is one special case where helicity and chirality are actually the same. And this is for massless particles. For massless particles, suddenly also chirality becomes intuitive because it's the same as helicity. And how does that fit to what I said before, that helicity depends on the frame of reference? Well, if my particle moves with the speed of light, and it does move with the speed of light if it's massless, then I cannot go to a frame of reference which moves faster. So I cannot, if the particle travels in that direction, I cannot go to a frame where the particle moves backwards. I'm always slower than the particle when it travels with the speed of light. So the statement that the helicity flips is not true for massless particles traveling with the speed of light. Then the helicity is anyway conserved, does not flip anymore for this particular example of a massless state, and still of course is intuitive, and it agrees with the chirality. So for massless particles, everything is intuitive, conserved, and Lorentz invariant. Okay, so this was the main thing I wanted to tell you. Questions?
What about massless particles in matter? Then they can travel slowly from speed of light.
Yeah, well, but in a sense they then effectively obtain a mass.
Yeah.
I mean, indeed, I mean, light, I mean, in media, light can travel with less than the speed of light, with less than the vacuum speed of light, and there is this famous Cherenkov radiation, which probably you refer to that because you know that one builds detectors out of that. Which means, I mean, if it travels, yeah, well, then you can have specific effects where you emit basically additional light from, yeah, as a kind of Mach cone, because you have this mismatch between speed of light and the vacuum speed of light. But you would then, I think, assign a mass to an effective mass to that particle for the fact that it's slowed down. Yeah. Yeah. So I mean, all this. I mean, what I said refers to vacuum because there a limit is set how fast you can propagate information. Maybe one other conceptual thing which I could have said last time, but last time we talked about other things. I started out, I mean, when I motivated all that, the construction started from mechanics to field theory. Of course, the simplest mechanics systems are free particles, and free particles are particles where no force acts on them. And then we switched to field theory, and I also talked there about free field theories. Now, a free field theory is actually something very different from an ensemble of free particles. A free field theory is when you can excite basically plane waves which do not disturb each other. A free field theory contains, well, second derivatives in time in the equation of motion, second derivatives in space, which basically couple these degrees of freedom to their neighbors. And this is something which is not what free particles would be. If I have an ensemble of free particles, say here in a row, then free would just mean, I mean, they all can move freely and do not influence each other. This is not what a free field theory is about. A free field theory is like a kind of rope. Fortunately, we have some here. I mean, obviously in here, each atom influences its neighbor. And I can excite some, well, that's not very good, but I can excite here some waves. Okay? Basically, this still, I still would think I described this cable here by, well, a free field one-dimensional, coupled always to its neighbors. But it's actually not free because gravity acts on it. But if I would switch off gravity, And actually in these oscillations one does not really see that gravity is acting in addition to what I do here. This still is a free theory except for gravity. Gravity comes from outside in addition, but that here the neighbors couple to each other, that's still fine with a free theory. So saying that the issue is that one changes a little bit the point of view, what is free and what is not. And one changes the point of view from the fields which can be excited to the excitations themselves. In classical mechanics one looks at 1 or 2 or 3 degrees of freedom and describes them. In a quantum field theory, the elementary degrees of freedom are indeed on each space point the possibility to excite something. But then what I call a particle, or what I identify in the end as a particle, is not this 1 degree of freedom per site which can be excited, but actually the excitation itself. So another example, not with a rope, but say with water, would be, I can look at a lake, and on the lake I can of course cause some oscillations. And what I now would call particles, what corresponds to my elementary particles, are these waves, not the water molecules. The water molecules have the property that they can be excited, and what I care about is the excitation itself. And when I have a wave packet, say, or I start to create a wave on the lake, this wave I call particle. This corresponds to my elementary particles. Whereas the water itself corresponds to the fields which can be excited. So I try to distinguish between the fields and the field excitations, which are the particles. The fields are not the particles. Like the water atoms are not the wave. The wave is a collective excitation of the water atoms, of the water molecules. And the atoms in the molecules. So keep that in mind when one goes from classical mechanics to field theory. The point of view changes a little bit, what one regards as free and not free, and what is in the focus what's in the focus of consideration. So what is then a free theory as compared to a non-free theory? Well, a free theory is if it has plane wave solutions, because a plane wave is something, a collective excitation, which is not disturbed by anything else. And plane wave solutions I get, now coming back to mathematics, if I have differential equations, say in space and time, with constant coefficients. And this in turn I have if I start with a Lagrangian which contains the fields maximally in squares. Because then when I derive the equation of motion, I hope you have tried to do that, to calculate all this stuff which is written down in the lecture notes. If I start with something quadratic in the fields and I derive an equation of motion, this is by a variational principle, so I basically always get rid of one field, coming from 2 fields to 1, which means I have afterwards a linear differential equation which gives me the motion, which means in turn plane waves are solutions of that. On the other hand, if I have a Lagrangian which has fields, either the same or different ones, in each and they have at least one term where there are 3 fields or more, this leads to an equation of motion which is not linear anymore. And then plane waves do not solve that, but one rather has now interactions. One has, well, waves influencing each other. So there can be, in a sense, collisions of waves, if you want, creating new waves. But this is then a non-linear effect, and this one calls interaction. This one calls interaction in the sense of a field theory. And I've tried to write down, well, just a few cases that you see what one can combine to meaningful interactions, and I also always said where, well, what is the physical significance of that? Does this resemble anything we have in nature? And well, actually, most of the things which one writes down, well, have something to do with the standard model, except if one constructs too complicated things with too many fields and so on. Then this is not related to the standard model, but typically these 3-point interactions, so of 3 fields together, this always or very often resembles what one writes down in the standard model in one or the other sector. So for scalars, like with the Higgs, or for vectors, like with the photons and gluons, and of course fermions, like with the quarks and electrons and so on. Sure, so now I don't know what else I should tell you. I think that's now a completely general remark. I mean, in the beginning I tried to set the stage on a rather elementary level, and of course I hope that you do not get bored here. Of course it will become more and more interesting, and next time we will look at symmetries, discrete and continuous symmetries, and then for quantum electrodynamics also look at local symmetries. So this will be then a very essential part of the lectures, to isolate symmetries and to deduce what one can learn from symmetry considerations. Because you have already seen in our first lecture, there are a lot of things, or I try to convince you that there are a lot of things which we, well, at the moment cannot, there are a lot of equations which we cannot solve exactly, so we need to develop approximations. And then symmetries help a lot to, well, to limit the work we have to do. From symmetries one can deduce a lot of useful things, well, which basically already restrict the system, give some constraints, and such that in part we can even qualitatively understand what's going on in a system without solving in detail equations of motion. And this we will use throughout these lectures to make use of symmetries in a very fancy way, essentially. So what else? Questions meanwhile? I mean, I don't want to repeat now the whole pages you had to read, because anyway you had to read it, and I don't want to take away from you the duty to read that. Okay? So I mean, if you want to learn something, you have to read it, and so I don't want to just repeat that. So in that sense, I mean, we can also stop earlier today, or you come up with questions.
You have these two different Lagrangians here in the beginning for the Dirac field. One that is Hermitian and one that is not Hermitian. And then you say that it's the action that matters for the equations of motion. And you try to show, you look at the difference of the actions, and you get some integral that you say is 0, or
Yes.
Or I don't know, or the important part is mainly when I thought about it is that you get some constant term, or I don't see how you get zero.
Okay, yeah.
But you get something that don't go into the equations of motion.
No, okay, there are two things. I mean that it does not go into the equations of motion. Of course, you could see that by brute force by going through that 2 times and see that the equations of motion are the same. However, the equations of motion only depend on the action, because the equation of motion come from demanding that the action has an extremum concerning this particular path, concerning, well, the fields satisfying the equation of motion and being not arbitrary fields. So in that sense, if I can show that the action is the same, the equation of motion must be the same, independent of whether one derives it well, in these 2 ways. Okay, so what I calculated was this difference here, and basically I have basically, well, rewritten things such that in the end I get this expression here. So I have a derivative acting on this object here. Was this here clear? All these steps? Yes. And now this here is these are derivatives, and then I integrate over it, which means I can use Gauss' law here. And Gauss' law relates then this to the value of this expression here in the brackets, evaluated at the boundaries.
Okay.
And the boundaries, I mean, this is a integral over all space-time. Basically starting, I mean, if we do that like in classical mechanics, it starts at some values which are not varied, at fixed values for a given time, and it ends at fixed values at the later time. So there is anyway no variation included, which means so there is no variation there included, and the spatial integral is over all space, which means that this here is 0 because I assume that at infinity there is nothing special left. That's actually an assumption which at some point one has to refine. I will come to that at the end, the very end of these lectures, when we talk about anomalies. This is not always true, this argument. However, for everything which is observable, this is true. We do not assume, well, we want to study something which is limited in space and time, and not influenced by something which is, well, extremely far away from the reaction we are studying, for example. So by Gauss' law, this here is related to, in a sense, to a 3-dimensional integral at a surface, and at the surface we assume that this here all vanishes. And therefore, this here is 0, neglecting surface terms. Well, basically it says this here is a total derivative. And yeah, when I integrate over, the result is 0. When I said the Lagrangian of a 1 is not Hermitian, the Lagrangian density is not Hermitian, Nonetheless, again, what matters is the action. The action is Hermitian. I mean, you see that the action is the same. So if one is Hermitian, the other must be Hermitian too, otherwise the difference could not be zero. The action is Hermitian, and from the action, again, I could derive equations of motion and then a Hamiltonian in the usual way how one constructs Hamiltonians. The Hamiltonian is Hermitian. In spite of the fact that I started with a Lagrangian, which is not Hermitian, but it's, I mean, not Hermitian in a very, very well-defined sense. It's non-Hermitian up to these derivatives, which are irrelevant in the action. And in that sense, or therefore, the Hamiltonian which one derives is actually Hermitian. So do not get the impression that from this particular non-Hermitian Lagrangian one also derives a non-Hermitian Hamiltonian. That's not true. Now, to be more specific, I should say the Hamiltonian density might be non-Hermitian, which I have not thought about. Probably this is Hermitian too. I mean, the total energy, the spatial integral over the Hamiltonian density, this must be Hermitian. The Hamiltonian density is also Hermitian, I think. Yes. But that's that's of minor importance. I mean, what matters is the Hamiltonian, which corresponds to the energy, the spatial integral over a Hamiltonian density. Anything else which was unclear? A, unclear, or B, so interesting that you want to know more about that?
Okay, now I didn't have time to read lots of spaces, but when you talked about this helicity and chirality, you said chirality as you can formulate chirality in a local way, but helicity only in a non-local way.
Yeah, you need. I mean, what I said was for the helicity. I mean, you need the momentum of the particle. And the momentum of the particle is something, I mean, you better you better observe it several times. You cannot, I mean, just by a snapshot, you cannot measure its velocity. You need at least 2 snapshots, which is non-local in time.
Okay.
So, I mean, in general, if something is sensitive to the momentum, and I mean, you do not need much information about the momentum. You only need to know in which direction it points. You don't need the absolute size, but nonetheless, I mean, you need to know something about the momentum. So again, you would do that by making 2 snapshots, right? I mean, I make a snapshot for my piece of chalk here, and a little bit later I make it again and I see it's here. Then I know the direction is like this. I even don't need to know when I did the second snapshot. I mean, when I know when I made the second snapshot, I could even determine the absolute size of the momentum. That's not so interesting for helicity. But I should tell you when I show you 2 snapshots which I did first. But again, to make sure that one has a theory which does not violate Lorentz invariance, which does not violate the principle that information cannot travel faster than speed of light. The easiest way to ensure that is to have local interactions. As soon as you start to involve momenta in addition in the interactions, that you involve suddenly information at one point and at a second one, or at one time and at a second time. Then you easily violate Lorentz invariance. I'm not aware that someone actually managed to write down something meaningful for non-local theories such that they are Lorentz invariant. This is extremely hard, if not impossible, whereas for local theories, I mean, this is just for free. There are in general some things which one can show this works very well for local quantum field theories, but it does not necessarily tell you that this is the only way of doing that. But at least it all fits if one does it like that. So local quantum field theories with the quantization conditions, which I formulated, not shown here, this is something for the quantum field theory course. That one, for bosons one has these commutation relations, for fermions anti-commutation relations. If one does that, everything is alright with causality and Lorentz invariance, which one subsums to microcausality, which says information should not travel faster than the speed of light. Or if some objects have a spatial distance from each other such that they cannot exchange information, then the commutator between these two fields should vanish, if these two fields are something which is related to observables. So what I wanted to say is, from a conceptual point of view, quantum field theories with these demands, they do the job. Does not mean that this is the only thing which has the potential to describe our world, but we came pretty far with that. I mean, it is a good theory, it has all good properties, and obviously we understand a lot of what the world is about, which understanding just means, well, we agree with the experiment. Whatever has been predicted from these meaningful quantum field theories also came out. Yeah, so for helicity one needs a non-local information, and that does not fit to a local quantum field theory, whereas for chirality, I mean, this is no problem. You just project with this operator which solely acts in the space of these four-component spinors. It does not involve any space or momentum information. Right? It's just these are 4 times 4 number-valued matrices, these projection operators. Whereas the helicity, you have seen, this involves the momentum.
Yep. I'm also about neutrino oscillation. Is this about if the neutrinos interact with other particles outside, or if the electron neutrino only change to another oscillations to mu neutrino, for example?
Yeah, so this is not about an interaction. This is more about whether you have the proper language of describing what's going on. Let me maybe let me first give you an example from mechanics. So suppose you have two penduli coupled to each other. Now I come with a lot of interactions, but I will in a moment discuss it away in a sense. So suppose you have the following situation. You have two pendulums, whatever is the plural, and you have a spring here in between. If the excitations of these guys in that direction are not very big, all this I can describe by harmonic oscillations. Okay? And harmonic oscillations translate to non-interactions in my field theory. So don't mess these interactions here up with well, interactions in the quantum field theory. So this is in a sense, first of all, a system which just lives on its own, undisturbed from outside. Now if I would look only on this guy here, now suppose I excite this now. And you know how that is if I excite, for example, if I fix this one, excite this, then first this, okay, let me do this here. First this one would, well, vibrate or swing very heavily, then via the spring, more and more energy is transferred to this guy, so after a while this will oscillate and can go back and forth, right? So if I only look for, suppose I only show you this guy here, then you would say, well, this motion of this guy here is very irregular. First it oscillates a lot, then suddenly it stops, then it oscillates again. You would think there should be a force from outside. However, if I look at the whole system, I don't need a force from outside. And especially if I look at the whole system, I can figure out two vibration modes, which basically are completely undisturbed and well, might mix with each other, but also, I mean, if I have one pure oscillation mode, this will not mix, this will not go into the other. And these oscillation modes are that either both vibrate in phase, or if, okay, I have not said much here, so suppose the masses are the same of these guys, I mean, then the second eigenfrequency is that it moves like this. And of course I can have a superposition of these guys and this is what I typically have when I excite this and hold that in the beginning. Okay, why do I say all that? First of all, I have two ways of looking at the system. Either I look at these two guys separately, at these two entities, what I always show you here, or I look at the two eigenmodes, this and this. The eigenmodes are much better to look at. They do not change in time. I mean, if I have this eigenmode here, this will not change in time. Same for that. So in a sense, concerning the energies, these modes, where I look at both particles, this is the proper language. Whereas if I look at this separately from that, it's not wrong to do that, but it does not catch this feature that I have a collective excitation here. Collective, either like this or that. The same is true for neutrinos. I can look at the neutrinos from the point of view how they are produced. This is like looking separately at this guy or at this guy. And to produce, well, the production process of neutrinos is according to the weak interaction, and the weak interaction discriminates between electron neutrinos and tau neutrinos and mu neutrinos. And this is like looking separately at these two, at one pendulum here. For the production this makes sense, and this corresponds maybe here to if you have a camera which only looks at this. It just does not see that. But to see what's happening concerning the energy, it's much better to look at the collective excitations. And the collective excitations, now in the neutrino language, are the so-called mass eigenstates. The mass eigenstates, if you want, are the collective excitations of the fields. These are the plane waves. And this corresponds to this collective thing, looking at both, at these two entities, if you want. So if I produce an electron neutrino, I already have a combination of this excitation and that, right? By the construction, by the production. But then these two modes behave independent from each other. So, in a sense, if I produce one electron neutrino, well, you know, I mean, we talk about quantum mechanics, so I should never talk about one single event, so I always look at a lot of events and can make a statement what happens on average. So suppose an electron neutrino would be 50% mass eigenstate 1 and 50% mass eigenstate 2. Okay, these are my mass eigenstate that correspond to these collective meaningful excitations. Then if I produce 100 times an electron neutrino in a weak reaction, in 50% of the time this would be a mass eigenstate 1, and in 50% of the time this would be a mass eigenstate 2. And this mass eigenstate 1 propagates with its mass, which basically relates its momentum to its energy. And in the other 50% of cases I have a propagation of mass eigenstate 2. Now I measure what's going on at a different point. Okay, so at a different point, again I make, of course, not one measurement, but say 100 measurements, because I mean, we talk about quantum mechanics. But my measurement will again be a weak interaction process. Of course, ideally it would be I catch my neutrino, put it on a scale and determine its mass. Then I would find, then in, say, with my example, in 50% of the cases, what I have produced is a mass state 1 type, and in other 50% mass state 2. But that's not what the experiments are about. We cannot catch the neutrinos and put them on a scale and measure its gravitational force, its mass, or say accelerate them and measure its resistance against acceleration. All that we cannot do with neutrinos. The only thing we can do with neutrinos is that they scatter on something and produce either an electron again, or a muon, or a tau, or at least transfer some momentum to what it's scattered on, so that I see something. And all these processes are again due to the weak interaction, which again are then sensitive to whether I have an electron neutrino or a muon neutrino and so on. So basically, so I produce now an electron neutrino. In 50% of the cases, actually it is mass eigenstate 1. This travels and is detected with a detector which, for example, is sensitive to electron neutrinos. Then I would again find, turning this logic around, that in only in 50% of the cases I would find that it's an electron neutrino. In the other 50% of the cases, it's something else. And the same is, of course, true for my other mass. And the issue is that now the wavelength of these two mass eigenstates is different. No, say if the wavelength is the same, their frequency is different because they have different masses. And therefore the interplay between these two fields afterwards projected onto an electron neutrino. This interplay can be different depending on which distance my detector has from the production point. And this one interprets as an oscillation, as a mixing. Mixing, it's only in the sense that one knows one has produced electron neutrinos and they are a mixture of these two mass eigenstates. But one can also reinterpret that and say, well, this electron neutrino mixes into, say, a muon neutrino and back. Coming back here, this would just mean, so, okay, so from what I told you, it should be clear, my collective excitations, these are my mass eigenstates, whereas looking at these guys separately, for example, this would be my electron neutrino and this would be my muon neutrino. Now suppose I can only produce this here. In other words, I can only excite this. I can never, suppose for a moment I cannot excite this guy in the production. So then I would also, well, kick this. And now this starts to move and also kicks that. But suppose my detector can only measure electron neutrinos. So you would never see this here. And then suddenly you would see, depending on when you measure that, you see very weird behavior. Sometimes you don't see an excitation at all, which means you would interpret that as, hey, there is no electron neutrino. Remember, it's the excitation, not that the particle is there. If this is not moving, because this guy which you do not see is moving, then you would say, I didn't have an electron neutrino. Well, I've produced some, but now I don't see it anymore. However, if you make a snapshot later on, you see it moving again. Then you say, now I have an electron neutrino effect. So you see, this is exactly these oscillations which one sees. Now not making snapshots at different times, but at different distances from the production point. But that's essentially the same because it's traveling. So spatial and time information is anyway correlated there. So electron neutrinos, if the detector only sees that, is just by looking at this sub-part of the whole system. The good thing is nowadays that we can see both, usually. So the key to understand what's going on with the neutrinos was, well, the first thing was that indeed we had experiments where we saw less electron neutrinos than what we expected. But this typically can have two reasons. Either I have produced less than what I think, or indeed they are gone somewhere else. So one first had to exclude this possibility that one has produced less. Or one needs a full picture and also try to see this. And this is what actually has happened. So there were experiments which were sensitive to electron and muon and tau neutrinos, and they have seen as many neutrinos, just the number, as one would have expected coming, say, from the sun. However, less electron neutrinos than what were originally produced. So it's not an interaction with something else, but it's really that in a sense you look at the wrong property. And you look at the wrong property because your production and your detection mechanism is sensitive here to only part of that, and not to the whole thing, or not so easily to the whole thing. Further questions? Otherwise we can also stop earlier. At least one is smiling about that.
I was thinking about how to formulate the question, but I don't know how relevant it is for this lecture. But when we use the Minkowski metric, is that under the assumption that the local curvature always is sufficiently small as it can be viewed as flat?
Yes.
So wherever conceivable.
Yes. How here this quantum field theory is formulated is in flat space.
Yeah.
So whatever we will calculate here close to a black hole, this would look very different.
Yeah.
Yes. Okay. So that's for sure. There are actually situations where one can have a mixture of that, to which extent one needs general relativity and to which not. And this is inside of neutron stars. So inside of neutron stars, also the gravitation is so high that you have to account also for the general relativity effects. Say when you want to know, one typical question in neutron stars is, how big is it? How big is it given a mass? So what is its size relative to its mass? And for that, basically, I mean, what you have to do is, I mean, you have to start out, say, centrally with some central density of matter there. And then you want to know, on the one hand side, which pressure does this matter create. So this is the pressure against gravity. And then which gravity does all that which is in this neutron star, which gravity pressure working inside does one get from having this mass there. And I mean, to calculate that, one actually needs effects from general relativity. It's not enough to do this just in a Newtonian way by equating the Newtonian pressure against the Newtonian gravitational pressure. However, so there one needs general relativity. Now comes where one does not need it. The relation between how heavy that stuff inside of the neutron star is and how much pressure it acts against gravity. This is the equation of state of that matter. I mean, this is a general statement. It's for every star, of course. The equation of state one can calculate provided one knows what's inside, whether these are neutrons or neutrons and electrons and protons and so on, or maybe in the interior is so dense that these are quarks. We do not know for sure. Anyway, one can calculate that microscopically from the interactions between particles. And there, one also might guess, well, but since this is now inside of such a dense object that the curvature plays a role, obviously, for this pressure balance it does. But actually it turns out that for the microscopic calculation, how does a given, say, blob of having a specific mass or energy, how much pressure does that have? How is energy density related to pressure? This is what the equation of state is about. For this, actually, one does funnily not need general relativity. One can do this with a flat g mu nu. I mean, one can try to calculate the corrections, and it turns out this is irrelevant. This is relevant close to a black hole, but even in the center of a neutron star, which in a sense is the second densest thing we have in nature, there it does not play a role to calculate the equation of state. So for a lot of situations concerning the microscopic properties, this flat g mu nu is perfectly fine. I mean, close to a black hole it's not. But otherwise, this is really good. To a good approximation, gravity typically is never that strong that it influences particles on their microscopic level. It might influence, as I said, this pressure balance, but this is more a mechanical problem of the whole stuff and not what's microscopically happening. But you're right, I mean, this g mu nu is really assuming flat space-time, completely neglecting general relativity effects. But they are small, really irrelevant. I suppose also in the early universe one needs a g mu nu, which is not flat. Well, I mean, this compares to a black hole in a sense. Further questions?
Kind of a follow-up, or
Sure.
maybe you kind of answered it, but if you would have a free field theory, would the predictions get progressively worse if you had extremely heavy particles instead of light ones, since gravity then would act up?
Yeah, but I mean now
Or would like mass scale be ridiculous for that to be important?
I mean, first of all, the Lagrangian describes. I mean, the Lagrangian has the potential to describe infinitely many identical particles. But it does not mean that infinitely many particles are there. It just has the potential to describe that you can have plane waves all over the place. But they are not necessarily there, right? I mean, so I mean, what you're after is not only the dynamics, telling you what does one guy do with the other, but in addition, in a sense, the statistics, how many of these guys are now there, right? I mean, if I have one particle in my whole universe, one non-interacting particle which has a mass, I would guess it does not influence itself. Whereas if I have two, and they are very heavy, then of course they influence each other by gravity. And then this becomes an issue, of course, and then yes, I mean, if okay, let me say yes and no. So first of all, if they are heavy, they influence each other more. On the other hand, the opposite is not true. If they are light, they still could influence each other provided their energy is high. Because gravity actually couples to energy, not to mass. Gravity also couples to massless states. I mean, we see that with the gravitational lensing, that photons are banded when they move around stars and galaxies. I mean, one sees these nice effects that suddenly one sees one galaxy twice because of photons going that way around some massive stuff and that way. So it's really energy which is attracted by gravity. In that sense, I would guess if I have if I have one particle which has a very high energy, very high momentum relative to a second one, and passes by closely, I mean, it also can have a gravitational effect, which grows with the energy. So yes, yes, so it's true, I mean, if they are heavy, they influence each other more. But it's not the only possibility that they influence each other more. Now you have to come with a gravitational question which I cannot answer. I mean, we are already close to my knowledge about gravity.
I think I'm out of gravity questions for now.
Then, should we close for today? Okay, then see you tomorrow, and there we will discuss symmetries.